anyway, neuroscience. So I got interested in pattern recognition. I made a model that got a lot of publicity at the time. I got invited to a meeting run by I don't know the name of the group anymore, but they published a journal called Daedalus, and they had a bunch of people who were interested in what was the brain like a computer. So I wrote a paper called Real Brains and Artificial Intelligence with Jerry, but mostly I wrote it. That was published in that issue, and to this day people come to me and say, that was a very interesting paper. That's where I said, the brain is not like a computer. You guys are all wet. You should be looking at neurophysiology and what's actually happening with neurons. And that was the time when neural networks were just getting started, and they said they were neurons, but they really were just some kind of little computational elements that added up a bunch of inputs and came up with an answer. So that was a very interesting stage in my life. We then got into robotics. We made a very simple robot that could track a light that moved around on the floor and do things like that. That was in the late 1980s, early 1990s, and it was around the time that Jerry Edelman was being recruited to go to the Scripps Institute in La Jolla. They actually put up a building for him to have his Neurosciences Institute there around the time that Rockefeller, I think, was interested in maybe having that space for other purposes, and so he moved. I was the only person in his lab who chose to stay here. I mean, I was one of two others who had tenure. The rest more or less had to move or look for another job. But I was very happy to stay. There were many reasons, but I ended up staying and forming my own small group. So one of the things I know you're interested in is how people get to start their own lab. Well, in my case, I moved upstairs, then moved a couple computers and some journal articles, and didn't get any equipment. I was never trained in neuroscience to stick electrodes in mice or anything like that. All my work was computational, so really the only, what I call a lab, is a room with some desks and computers. So that was easy. I attracted a postdoctoral fellow named Alan Koop. Alan and I was particularly interested in studying how the brain controls movement, again, because of music. I always wondered about this question, as a student of the piano. You sit there, you start a new piece of music, you read the notes, you play this da, 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 and then as you learn it, it goes faster and faster, and finally you perform it. Well, what changed in the brain? The speed of impulses down a neural axon does not change. The speed of opening and closing of ionic channels in a neuron does not change. The only thing that could have changed to allow you to play faster is the pathway through the system, eliminating some connections that were necessary during the training period. So I wanted to work on that, and so did Alan. Well, so we knew the cerebellum was important in movement, and we made a model of the Purkinje cell, which is the main output cell of the cerebellum. We published some work on that. At the same time, we got interested, I don't quite remember why, in analyzing from the information theory point of view, how much information did the spiking of a neuron convey to another neuron. And I had an idea that I'm still pleased with, that I don't see other people using very much, to basically get around the problem of never having enough data to count to calculate information. You need to know what are all the possible patterns that can occur in some temporal sequence, and then what are the frequencies of these various patterns. And of course, Claude Shannon at Bell Labs had published his famous work on information theory, and the formula was well known. So my idea was to fit the distribution of interspike intervals with an analytic function. It turned out to be what's called a gamma distribution. And then by integrating that function, you could calculate the Shannon entropy exactly, effectively interpolating between the data points you had by doing this fit. So we did that. Alan stayed with me 5 or 6 years, moved on. I began to attract a few students. Basically, we worked on anything that a student was interested in, that I was interested in. I always felt, and I still feel today, that you should not just have a degree in computational neuroscience because you're going to have trouble getting grants and jobs. It's better to have some actual experience with an experimental system. So the first student I worked with me and Charles Gilbert, made a model of early, what's called V1, the first stage of visual cortex. Got results that matched some of the experiments that Charles was doing. His name was Valentin. Valentin also did some functional MRI studies at the same time, and so he got a very good introduction. Another student, Cameron Wellick, was interested in birdsong. He did a thesis with me and Fernando Nottebohm. He recorded young birds learning their songs up at our Millbrook Research Center and wrote computer code to analyze. He had more recordings than he could listen to in his whole lifetime because he was recording these birds 24 hours a day, and he had several dozen birds. So there were, it was just, the computer had to listen to all these recordings and tell you where the interesting parts were. Both of these students went off and did not go into science, I'm sorry to say. They're working in some aspect of computer tech. A third student came back to my interest in the cerebellum, Ben Campbell. He left Rockefeller without finishing his thesis, I'm sorry to say. I believe he's also working in the tech business these days. But those are just some of the examples. I'm currently working with an anesthesiologist at New York Hospital named Kingsley Storer. Kingsley, is an employee of the hospital and spends most of his time putting people to sleep for a living. But we've published some very interesting work on how this drug called propofol works and what effect it has on the brain. And for most people, that's the one anesthetic drug you've probably ever heard of, because of Michael Jackson dying from it, and it's a very toxic substance that has to be used very carefully, and we're trying to study some of the mechanisms of how it works. So that's that, and I'm also currently working with Charles again and Vinrik Freiwald here, who works on face recognition, and so we're doing some studies on how we recognize objects and what are the parts of the objects that are most important to the recognition process.